So hey everyone, so today what I want to be talking about is this like sort of like these two simple tricks that can let you implement pretty much like any algorithm or data structure in Python. Python has two abstractions. Like one is the list, right? So you may be familiar with this one. So it's like a list, right? It has like a bunch of elements in it. And then another one is so you can just like print this, see what it looks like. And then another one that's is very it's very common to use is a dictionary. So what a dictionary looks like is it'll be like, let's say like B, then it uses like these squiggly brackets. Let's say you could say A. So this is the key, and then this is the value, and then let's say this is another key, and then this is another value. This is sort of the syntax for this, right? So let's say if it prints B, what do we get? Right. So what the colons really mean here is like we're mapping a key to a certain value. Right. So basically, what I want to make the point today is that using these two simple abstractions, there's a couple of algorithms that, like base data structures, excuse me, that we can build pretty much for free. So I'm going to show you how to do sets, and we're going to do binary trees. We're going to do graphs, right? And let's see, is there anything else we could do? Maybe we'll do a heap, I don't know, depending on how much time we have. Right. So what's a set, right? So a set is, um, so it's a built-in Python data structure initially where let's say you have one, two, right? Python set. Let me just make sure what the library is so I can just compare it to show you why the behavior is the same. Print set. Yeah, sorry, it's a little less. Okay, so it expects like a single argument. Okay, so what happens if we print A? So you see, like it basically makes all the elements unique, right? So this is sort of what a set is, and then there's a few operations that we want to have on sets, right? So let's think this through. So really, to implement a class for a set, well, you need to basically have this like unique property, right? We also need to be able to add elements. We need to be able to maybe remove elements, right? And then also maybe like more advanced is like let's say looking at set intersection. So given two sets, which elements do they have in common? So given two sets, which elements do they have in common? So, it seems like a simple problem. It sort of gives you a good idea of how like library level data structures are implemented. So let's just sort of, go through this. So let's say we have this, and it's called like my set, for example, and we're going to define some sort of init function. And then literally the functions that we would add would be the stuff that I said, right? So like we have an add function, we have a remove function, and then we have some sort of intersection function, right? So let's think each of these through. So the init function, like remember, like the topic of the stream is like really everything's a list or a dictionary. And so let's just do that, right? So let's say we have self dot basically dic. Uh, so we have basically some dictionary that we're initializing, right? And so then we want to add elements to this dictionary. So one way to do it is to say, okay, well, basically, let's say here you want to add like you're adding a number, right? So let's say you're adding some num, and we can annotate stuff in Python just to say this is an int, but really this could be anything, right? It's just like to make the point a bit clear. Actually, maybe let's remove this constraint. Like let's say element, right? Because this could be a non-numerical thing. And so then what I want to say is, okay, well, I want to be adding this thing. And so really the simple way to think about it is to say, well, self dot dic of lm is equal to true, right? So, okay, so that's interesting. So, but now like, we don't have the sprint thing, right? And so, we can't just like run, for example, let me just skip ahead. Let's say we can't just say something like set, my set equals my set, and then we want to say like my set dot add one, then my set dot add two, And then we want to say, sorry, my set dot add one, right? Because we want to make sure the elements are unique. And then we want to say something like print my set, right? So this is sort of what we want to do. And this is not going to work, right? And so we just need to think about how this is going to work. Like, one, we don't even have a print function. Well, the nice thing about Python actually too is that a print function is really you can print any class in Python if you overload this function called represent. Um, so what does this take, right? So this takes self, this takes self and element, this takes uh, self and element again, and then this takes self, and then this takes self, and it takes another set, which is basically of type my set, right? So this is just sort of a good way uh, set to second set, something like this, right? So this is sort of like, so you can sort of see just like by setting up like the classes this way, we've already somewhat answered our questions here. And so let's see, we can here return not implemented, right? And then here return not implemented, and then here just like until we do these. Okay, great. So let's think about this. So, well, first off, we said we're going to keep track of a set as a dictionary. And so we have a new element and then we just add it to true, which also means that uh, if we have more than one element, it's going to get overwritten. So that's actually perfect. So really here already we've done the basic functionality, right? And so another thing here to keep in mind is like, okay, well, let's say for the represent part, because this feels like the important part. Like, so you can in Python you can print uh, the dictionary keys. This is very practical here. Like this here, I'll just zoom in a bit. But you can say, well, for the key and value in my dict iter items, you know, print the key and value, right? So here in our case, if we go to represent, so first step is first thing is called dict here, and then okay, but then we don't really need the value, right? We're just only printing the keys. And so what you can then do is you can say, okay, well, I'm gonna iterate over all the keys, and then I'm gonna basically set up some sort of list, basically here. Like let's do it like this. Result equals like this, for example. Like, again, some sort of list, right? So this makes our life very easy. Now I want to say like result dot append key. And then I want to say, actually, no, maybe we could does this work? Let's say if I just say print key. All right, does this work? So now let's say I have add. Yeah, so this should work now. Let's see. So name my set is not defined. Okay, that's fine. Name my C is not defined. Okay, my set. Name dict is not defined. Um, yeah, that's true. So let's say self dot dict. Dict object has no attribute iter items. Oh yeah, I see. So now I think this is like a Python 2 versus Python 3 thing. So let's see if this works. Int object is not iterable. So Python 3, to iterate the dictionary. I believe, yeah, it was items maybe. See, does this work? It was something, yeah, that worked actually, right? So it basically printed 1 and 2. But for some reason it's failing, right? So let's see, why did it give a syntax error here? But it seemed to work because string returned non-string type non-type. Oh, I see. Um, So let's see how people typically do this, like represent Python string. See what's a better way of doing this. I guess like just saying like string of the whole thing, right? So maybe if I do this, I can say result dot append key, and then I can say here return uh, string of result. All right, and yeah, so you see this works now. So we've already implemented a set, just at least the addition part. So we can sort of, uh, you know, oh, interesting though. So let's say, so how would remove work? So would remove, yeah. So what we want to do then here is we actually want to add one more detail. We want to say, well, if actually, yeah. So we do need the value. Okay, great. So we want to say basically if val yeah, equals false, if equals true, then you append. Otherwise, you don't append, right? And so similarly here, basically what remove is going to do is it's basically just going to go um, and say, well, self dot, you can do it in two ways actually. So you could say self dot dic of lm equals false, right? So this is one way of doing it. And the other is just straight up removing the key. And let me see how to do that. So Python dictionary remove key. Oh, I see. So if key and my dict, uh, then delete my dict key. Interesting. So let's see if this works. Okay, so basically we want to say if lm in self.dict, then I want to delete um, dict and then lm, right? So let's see if this works, right? So we added the one twice. Now I want to say my set dot remove one. So dict not defined. Okay, and lm and self dot. Okay. All right, so this works here. So we already have a remove right now. So this is good. So with intersection, basically what we're going to do is we're going to have a second set, right? So now we're going to say, okay, well, we have a second set equals my set. And let's say, let's remove this 1, 2. And then in my set, everything I'm going to do is I'm going to set my set add dot 2. And then essentially when I say uh, my set dot intersection, so second set, and I want to say you should use try error to raise an error if it is not in the set. Um, yeah, let's think about that, right? So yeah, so then if lm is in the dictionary, then do this. Else, so I don't necessarily want to print an error because I don't want the program to crash. So maybe um, also if val is much cleaner. Yeah, so you mean here, right? Like in this part. Yeah, like if val, yeah, I agree with you. And then here, okay, yeah, so let's see here. Hey, thanks for joining. I appreciate the tips. So let's see. So now with intersection though, it's like okay. So I have the second set, and I'm adding something to it, and then I want to take the intersection of the first set with the second set, and basically this should return 2, right? So if I print, uh, uh, yeah. So basically, I'm gonna call this the intersection, and then I want to print the intersection. So this also needs to be a set, right? So what I'm gonna do is I'm gonna say uh, intersection intersect equals my set, right? And now let's think about this, right? So we want to be iterating over the one dictionary, and then we check if the keys exist in the other dictionary, and if they do, we add them, right? So basically, we want to say for uh, uh, key val in self dot dic dot items, right? So if key in second set, right? Then what we can do is we can say, okay, well, intersect dot add uh, key, right? So this should work. So expected an indented block. Why? What happened? Oh yeah. So else, what's reasonable here? Like I think uh, I sort of want to just like maybe print something. Like I just want to say something like print uh, basically element dot format does not exist. Something like this. So argument of my set is not iterable. Oh, that's interesting. Yeah. So this is sort of yeah. So we need to create an iter class here. So let's do that. How does this work again? Iter Python. A pass is a silent failure though. Like you do want to have something. What are these like suckies? Oh, I see. So I need to implement next as well. Hmm. It's okay. I think this is something we can get back to. But basically, here just one thing to keep in mind. Um, because I could always turn it into a dictionary and do something hacky like that, but sets need to create a custom iter function. But hopefully, like I think this example gives you a good idea of like why I like Python dictionaries so much. Like it's just like it's just a data structure that doesn't seem like it necessarily is related, but you can just make it work. So let's do binary trees next, right? So with a binary tree, let's think about this problem for a sec. So in a binary tree, what you're essentially doing is like you're gonna have like let's say some value like here 3, and then everything to the left of it is gonna be smaller. So let's say this could be like 1, right? And then here, forgive my ASCII art skills. Let's say this is 5, for example. So basically, we're gonna have a couple of things, right? So we have this class called a node, essentially. And in this node, like what do we have, right? So we have define init, and the node has basically uh, three things it needs, right? So it has val, left, and then right. So you have self dot val equals val, self dot left equals left, and then self dot right equals right. Right. So this is what it looks like. Um, so yeah, that seems about it here. Like maybe we could also have like just a way to print these nodes. And in this case, this would just be, let's say you would have let's say a string, right? So let's figure out how to construct the string. So we're gonna have a return um, a string where a val, and then you have 0, uh, left, and then 1, and then right 2, and then say dot format val left right. This work. Right, so let's say now I make a new node, a node like let's say 5, 3, 2. Val is not defined. Oh yeah, so this is gonna be self.val, self.right, and then self.this. This should work. All right, great. So hopefully this gives you a good idea of like also how to implement like your own print functions. Like I actually really like this trick in Python. So this is sort of a tree, right? So let's say we want to, so then a tree basically. Um, well, sorry. So this was one way to do it, and another way to do it is, for example, you could say, well, let's say I have node one, and this is going to be a key value pair where you have val, and then what it should be equal to. Let's say 5, left, I don't know, 2. Is that what I did? No, so I did 3. Then I said this was 1. And then right, this is 5. Right? So say now if you print node 1, what do you get? So you also pretty much get what you expect. Like this is obviously like a lot less code. So let's think about like what we can do with this, right? So now let's say we want to create a tree, right? So what's a tree? Um, is basically just like when you think about it, like if you want to do something like an init function, it's basically self dot nodes, where you have a list of nodes, and then you basically want to add a node. Um, so you'd basically say, okay, well, I want to add a node, and then what this essentially does, it does self dot nodes dot append node. So you may be thinking now, okay, great, but this doesn't guarantee. So this is just a tree, right? Like this is not a binary search tree. This is not like it's closer to a graph actually, like the way I've defined it here, because a tree is just a graph that goes in one direction. But let's think about like what like can we do some interesting stuff with this, for example? So one way to figure out like one interesting thing that we could do is say, okay, well, is there a path, right? You know, let's say so given two nodes, uh, is there a path linking them? Right. So let's think about how we could do this, right? So let's say so in the tree class, you're basically going to do a search, and then you have yourself as a reference to the data structure itself. Then you have a start and you have an end, right? So we want to figure out if there's any path that exists this way. So basically the way the way this would work is you ask yourself, one, does the start even exist, right? So basically, um, so left uh, and right is equal to nodes of start, right? And then no, wait, how would this work better? Yeah, sorry. I see. I already made a mistake here. So instead of having the actual value here, I want to have the essentially the node name like this, and I actually want the key to be a list, and I want this key to essentially have the current value, and then the left See, this doesn't make much sense here. 532. See, it doesn't matter too much because it's not a binary search tree. So let's say it looks something like this, and we print this as current value, left value, right value. But yeah, no, fuck it, let's make it like this. So this is 3, this is 1, this is 5. You see, it's still totally okay to do something like this. Right, so, well, what are we doing, right? So we're gonna say, well, next node, like the next nodes that we want to visit, uh, is basically gonna be equal to self.nodes of start, where we skip the first element. Right, so let's say, let's just print next nodes just to make sure this works. And then I'm gonna have a test case where I say, um, yeah, so I'm gonna have, let's say my tree equals tree. Then I'm gonna say my tree dot add. So I'm gonna have node 1. So yeah, maybe this would be easier if we wrote this like this, I think. If we said this, right? So 3 goes to 1 and 5. And then here we could say something like, well, 1, uh, sorry, no, 5 goes to, uh, let's see, 4 and 6, right? So, sorry, no, it should be like this. All right, so this works great. And so basically our next nodes, like our next candidate nodes for the search, are going to be all the nodes that start at the starting point, right? And so let's see what those look like. So we have, like, let's say we add node 1. So I'm going to call this node 2. Okay, right, so we add node 1, then we add node 2. And what I want to say is we want to search my tree dot search. So we want to see if there's a path between, um, so in this case, what I want to do is I want to see if there's a path from 3 to 6, right? And yes, there should be, because 3 goes to 5 and 3 goes to 5, 5 goes to 6. So this should return true eventually. So what does this do? So given 2 nodes, is there a path linking them? Okay, sure. So tree is equal to my tree, sure. So this thing takes 1 positional argument. Yeah, so it means things itself as well. So the int object is not subscriptable, right? That makes sense. So yeah, so start is an int, right? So let's see. So we want to check out nodes of start. Okay, and then list index is out of range. Well, actually, no. So it's not self.nodes of start, nodes.append. Okay, right. So we're just appending these nodes. Um, do we even need to keep track of the nodes this way? We just have a dictionary of nodes. So the oh, I see, I see. Okay, okay, got it, got it. So let's do this instead. So instead of having it be this way, we'll say this is 5 and 4, 6. Right, so this will be our tree actually. Okay, right. So our tree is just a dictionary. Um, and we're gonna initialize it just based on a dictionary here. Um, so instead of this, we're gonna say this, and then give this, and then this. Put this here. So tree object has no attribute node. That's right. We're gonna get rid of the add function for now, or no, we could add it actually. So the way the add function would work uh, is that we're gonna need a node, uh, like basically a parent, and then we need left and right. And so then what we're gonna say is that we're gonna essentially uh, so say self dot tree of parent is equal to a list which has left and right. So this makes our life very easy if we want to add new elements. And again, you see how like everything's a list or a dictionary. This is one of the big mind-blowing moments I had programming in Python a couple of years ago. But yeah, so you do this, and then okay, well you want to search for a node, so you start doing this. So how are you gonna make this search work? So first off, let's see, does our printing even work? So tree object has no attribute nodes. Okay, great. So I think this changed quite a bit, right? So our next nodes are really just gonna be so yeah, so there's no more nodes. So we're gonna say self dot tree of start, and then we're gonna print next nodes. Okay, so this printed 3 for some reason. Okay, so it printed 3 self dot tree dot start. All right, so start is gonna be equal to 3, and so I've wanted this to print 1 5. And so why is this giving me a key error as well? So am I doing something weird with the here? So 3 6. So let's just check what my tree looks like. Okay, so this is failing here, and then there's a key error. And because my tree dot search is tree of tree, okay. And that's when I come to search, I'm saying I want to look at the start. What does the start contain? So start is just 3, right? So let's say I'm just gonna make my life a bit easier. So I'm gonna say print, uh, you know, so start, and then I'm gonna say next nodes print this, and then I'm gonna say dot format, and then I'm gonna say start and next nodes. So it's sort of giving me a key error. It's saying the key doesn't exist at all. And this is because it's saying, well, self.tree of start doesn't really exist. But I know that it does exist, right? Because I know that maybe if I just define tree on top just to double check. So if I do this, make sure tree works fine, then do this, then do this. Does this work? It does not. So why is this not working? So my search of tree of 3 6, and it's saying 3 doesn't exist. So what if I just print the tree then? I mean, remember you can do this because it's a Python dictionary. Okay, so we're getting, this is interesting. So we're getting an empty, oh, I see. Okay. Okay, great. We found the, we found the bug. This was dumb. But yeah, the bug statement helped, I guess, right? So Okay, so this is great so far. So, well, we have like these candidates now for next nodes, right? So what do we do with these, right? So remember, there's sort of two ways of searching, right? So uh, one is BFS and one is DFS. So this is breadth first search, and this is depth first search. Right. So the reason these matter is because we're gonna say, well, we want to put these nodes uh, in a queue or dictionary. So we're gonna initialize, like, let's say our queue, and again, our queue is a list. And so the way this works is we're gonna say queue dot append next nodes. Does this work? Okay, just like let's just print the queue to double check that this works. Okay, so I actually don't want it to have like a list. I just want to flatten this. So maybe because next node, I'll just do this. I'm sure there's an easier way to do this. Next node of one. Okay, right. So now it's flattened. So this is great. So far, you've noticed that like, well, we have this queue and we're starting to consider elements from the queue, right? And so what we want to do now is like, remember how a queue works. So the first element, it's first in, first out. So basically, the first element that I append is the one that I want to be popping, right? So if you look at, let's again look at how you print the queue here. So because, or wait, why was one? Oh yeah. So yeah, so this means that we want to basically pop the left hand first. I appreciate the subscribe, Foxtrot. Thank you. Let me know if you have any questions. All right. So what I want to be doing here is I want to be popping this side, right? So let's just see if that works. So like in Python, pop first element of a list. Let's see how that works. Because there was a pop, yeah, pop zero, and pop zero pops the first element. Yeah, so this is what we want, right? So like what's really practical about Python is that here. So look, this is a list, right? So now I can say uh, basically q dot pop zero, right? So this is going to be the base. So we're going to need some for loop, like basically while q not empty, right? So something like while I don't know how this would. Let's just say length of you know list not empty. I think this should work. Oh, if not a, I see. So yeah, so while yeah, so yeah, so while q, what we want to do is we want to pop the element of the queue. And then what we want to do is we want to say, great, let's start searching over its neighbors, right? So you pop the queue, um, and then like let's say this is going to give you, let's call this the next node. And then what you want to do, this is going to give you a single element, and then you want to append to the queue. So yeah, so once you pop this element, you want to say if next node equals to ends, then return true, right? Else, what you want to do then is you want to start looking at the neighbors, right? So you want to say, um, so you want to say great. I want to then say next node. Uh, sorry, q dot append, and you want to append to this queue two things like next node of so yes, you want to say tree of next node, right, of zero, and you want to q dot append tree of next node of one, right? So, and you recurse, right? So after you do this, you pop again, and then you check, and then if you get to this point and then you don't see anything, then you return false. And this was BFS here. Um, I'll give you a cool tip. If anyone can chat can figure it out. There's one line code change you can make here, and then you can get DFS. Actually, one character code change. I'll let you figure it out. So this is basically, like here we could even, let's say, even add it as an argument. So we can say something like BFS and say this is true, for example, by default. And then basically what you want to do here is you want to say, let's say, actually, I'll make this DFS. I'll make this false. And yeah, so here, like what you want to say, where was it? Yeah, so here. Do you want to say if DFS next node is equal to q.pop, else, that's it. So you see here, like we've implemented, so like I shouldn't call this tree anymore, right? I should just call this graph maybe. Graph, uh, graph, graph. Okay, parent. I mean, yeah. So it's a graph with only two possible neighbors, but so maybe I'll call it tree again, actually. But the same idea, like here. So let's say we want to extend this work even further. See here, we go to next node, q.pop. So this would pop the last element, and this pops the first element. And I think it's either this or this, because this is usually how you do the last element in Python. But I personally found this very cool generally. Like, okay, well, you have this exact same code, and then just transitioning it from DFS to BFS is a single line code change. And it mostly comes down to how are you popping the first element or the last element that you're adding? Otherwise, you're just gonna keep checking like this next node. And if you find it, then it's true, and then you just keep iterating like this. So another way to imagine this is like, well, imagine that this tree now actually had like an infinite, like let's say had 10 possible neighbors, like it didn't have two. Well, actually our search code works just fine, but what we would need to do is maybe change this to, like basically instead of this, you would write this as uh, for a next node in next nodes, right? And then you would say q dot append next node. So this is how you would deal with like more elements. Like that's it. Um, yeah. So let's see. So one last thing. I don't know. I don't really feel like talking about heaps too much, but maybe we'll do binary trees because that's sort of interesting. Um, let's go here. Yeah. So what's the difference in a binary tree, right? So the difference with a binary tree is that when you're adding stuff. So let's just focus on the add part for now. So really, the key thing in a binary tree, like sort of like the invariant, right? Let's just do this mathematically. Basically, so let's say you have a bunch of nodes. So it's diff init and self, and then let's say you have self dot nodes, right? And this is again could be some dictionary. And we already said that this dictionary. So let's see, this is tree. Right, so we can use the same tree as before. I think this was a good example because this was already a binary search tree. And so by default, this is already a binary search tree, right? And so now the question is we want to add a new element. where do we add it, right? So how do we keep the binary tree invariant while adding stuff to this dictionary? So what's the binary tree invariant, right? Like the binary search tree invariant is that basically for all nodes, uh, yeah, actually maybe I'll just write it this, like basically left smaller than val is smaller than right. So this is what's always true, right? So we can make sure that like when this is first called, we can certainly say, okay, well, this is going to be true. But let's say now, let's say you want to add something, right? So we want to say add, and then you want to add a new node. And so what's a node, right? Like a node is really going to be it's also going to be a dictionary, right? Where the value is the like you have the value. Yeah, so we're actually just adding a single value, right? And so what we want to do is we want to say, okay, we want to start at the root of the tree. And so this is something here that's not entirely clear where the root is. And so it could be useful, for example, to just say something like, root, and then it's 3, right? So you see, like, it's sort of like very hacky, but it gives you like this unstructured way of making like very complex data structures if you want. And so you can say, okay, well, great. So I have this root. Um, Actually, does this work in trees? Can dictionaries have like heterogeneous return? I believe like they can have heterogeneous types, if I'm not mistaken. Let me just double check. Yeah, they can. See, it's amazing. It's like completely. It's like a JSON object. Like think of it that way. You can just return whatever the hell you want. Import JSON and then JSONify. Three. Oh, we need to pip install it. Never mind. Do import JSON? So yeah, Python JSON. It's not super important. I was like curious about how to do it. JSON.dumps. Okay, JSON.dumps a dictionary. I see. Okay, so then JSON.dumps. Right, so this could literally just be let's see, they can do it in HTML or something. All right, so again, like JSON is really just also like think of it as a dictionary, and that's also what makes like web protocols really easy. The fact that you can send arbitrarily complex data structures as dictionaries, and again, like we've seen, like we can do graphs with dictionaries, you can do sets. It's very useful to use lists like as well inside. And so really now with this addition, basically, well, we're gonna start with the root, right? So we're gonna say root equals node of equals self dot tree of root. Right, so this is the first element, right? So then we want to say while next node, uh, yeah. So while this next node exists, uh, what we want to do is we want to check. Okay, well, like one, should we go left or right? So one is the current node if node is basically, I'm gonna call this not current node, right? So then we want to say current node equals root, right? Oh, hey Kristan, how's it going? Well, this is a weird stream, but today I'm sort of talking about how you can implement all data structures you want in Python only using lists and dictionaries. So we went over graphs, we went over sets, and now we're doing binary search trees, and I'm probably going to call it after this. So I'll be sharing the notebook in the description, so it should make this pretty clear. But I just like generally really enjoy, like like I feel like doing data structures is much easier in Python in general. All right, so let's see. So while current node, if basically a node is, yeah, so if node equals current node, right, then do nothing, return, right? If node is greater than current node, then next node, then current node equals to current node, and then you go to the right, right? And so otherwise, else current node equals uh, current node of 0, right? So this is how we're doing the traversal. And at some point, we're gonna get to null, right? When we get to null, and so we know that this is where we want to be. Uh, yeah, actually, yeah. So then we want to keep track of the last node. So really, what you want to say then is current. Yeah. So we want to say something like current node of no. So current node. Yeah. So this is interesting because this may crash actually, because this is not always going to exist. So no, here if the node exists. Oh, I see. I see. Okay. Yeah. I think we'll put it here. Uh, what's that? Return error. I don't know. Return print something went terribly wrong. Right. So we want to say is that okay? Well, if node is less than current node, if current node one doesn't exist, then what you want to say is current node of one equals node. Else current node is equal current node plus one, right? And same thing here. Like if uh, yeah, so else if not current node of 0, uh, current node of 0 equals node. There's no node 1. Else current node is equal to, right? Okay. So let's see. So then, and if we're here, uh, yeah, and I guess if this operation succeeded, you can also return true. So I think that is going to be it for me today. So what I sort of wanted to go through was show you just like based on these sort of very simple built-in data structures in Python, like lists and dictionaries. You can use it to do more complex stuff. So set, for example, is a built-in class, and there's a couple of stuff you may want to do on a set. Like you may want to check unique elements, you may want to add elements, remove elements, take the intersection between them. And so we can sort of like think this through, right? So you can create your own custom class that has a dictionary, right? And then basically for each new element that gets added, if it's true, that basically means it's in the set. Then you can also delete elements from the set. If you want to represent, like as in like print the set, you can just basically create a string with all the keys and values. So this is a very useful pattern. So you can also iterate over dictionaries, not just lists. So with list, this would be for key value and enumerate of list, and then in dictionaries, it's in self dic of items. Um, Similarly here, if you're doing an intersection, what we can basically do is keep track of a separate set, which is just an intersection, and if they share keys in common, then we can add them. After that, we talked about just in general, like this is how you would generally do in a more object-oriented way, represent like something like a graph or a tree, where you would explicitly have the left and right node. But the point I'm trying to make here is that, well, you can also represent a tree just as a key map, right? Where the value is the node, and then and then the key is the node, and then the value is its list of neighbors. That's useful because it lets you initialize a tree, it lets you add elements to this tree, and it lets you do a graph search. And the really nice thing, a trick that I learned a bit too late, is that the difference really between DFS and BFS is very trivial. Like it's one line code change where you're adding nodes that you're considering to a list. And if you're popping from the beginning of this list, you're doing BFS. And if you're popping at the end of it, then you're doing DFS. So that's it. And similarly, if you want to do something like a binary search tree, you could also just navigate like this dictionary. You could like, like dictionaries don't have a requirement where the root, where the keys and values have to be of the same type. So you can basically just encode arbitrary data as you, the same way you would do for something like JSON for web protocols. And what you could do is then you could just like, let's say, given that you have a binary tree, you can add nodes to it by repeatedly adding these nodes. And then there's still sort of like a rebalancing algorithm that we didn't talk about, but then that's sort of like a good segue into discussions like heaps or red black trees, which I'll probably talk about some other time. So yeah, so that was it for me. I hope you enjoyed this. Like I certainly did. I've been wanting to talk about this topic for a while. So yeah, stay tuned. I'll figure out what I want to be talking about next. Thank you, everyone.